An urgent alert from the most distant edges of our solar system. A comet codenamed 3I Atlas is exhibiting bizarre behavior that is nothing like a comet should. It all happened too fast. Just days ago, as astronomers watched it breach a critical zone, this visitor from another star system began to brighten uncontrollably. This completely surpassed all the wildest predictions. Its ghostly atmosphere has already swelled to a terrifying size. Large enough to swallow half the sun, its glow has for some unknown reason shifted to an unsettling, eerie green. But the strangest part is yet to come. It has grown an anti-tail pointing directly at the sun, completely defying the laws of physics as we know them. Now it's hurtling towards Mars at an insane speed, and the top scientists on Earth can only admit they are completely baffled by what's happening before their eyes. The countdown to its final destination has begun. With every passing hour, this mysterious interstellar wanderer looks less like a comet, and more like a giant cosmic question mark hanging over everyone's heads. So please be sure to stick with tonight's exploration until the very end. You will see what happens when alien chemistry, dormant for billions of years, is awakened by the sun, subverting everything we thought we knew. Part 1. It's out of control. It's getting bigger and brighter, like a waking beast. The cold, hard data doesn't lie, even when the truth it reveals is beyond imagination. The time is mid-September 2025. Astronomers monitoring Comet 3I Atlas discovered some hair-raising signs within the tedious data. Its brightness measurements began climb wildly, far outpacing the prediction curve, soaring from an inconspicuous magnitude 16 to a staggering magnitude 12. Perhaps you're not familiar with astronomical magnitudes, and that's okay. All you need to know is that this is an extremely terrifying change. Let me give you an analogy. In astronomy, the magnitude numbers work in reverse. The smaller the number, the more terrifyingly bright the object is. A mere 2 magnitude difference means the light it's now emitting is a full 6 times brighter than astronomers had predicted. And this brightening isn't gradual. It's accelerating. A database dedicated to tracking comets, COBS, began to be flooded with bizarre data points, steadily breaking above all normal curves for a warming comet. Every telescope on Earth confirmed the same unsettling trend. All the sophisticated models astronomers had built for it were now being ruthlessly crushed, one by one. The decisive moment occurred in early September, when the object breached a critical distance 2 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 50 million kilometers. In other words, Comet 3I Atlas was still twice as far from the Sun as we are. Yet right there, something fundamental and unknown happened. The frantic acceleration in brightness was completely unexpected. More accurately, its intensity had reached an alarming level. What exactly caused this bizarre surge of light? The most plausible explanation is that the strange ice crystals and compounds, locked away inside it for billions of years, have awakened. Under the scorching heat of solar radiation, these materials from another star system are not just melting, they are violently exploding, sublimating directly from solid to gas in a way we've never seen before, kicking up a massive dust storm that frantically reflects sunlight back to Earth. But this perhaps is what we should really be worried about. This kind of runaway brightness often signals extreme instability. Comets undergoing such sudden changes are very likely to disintegrate on the spot, turning into a spectacular cosmic firework display. They might also be a flash in the pan, quickly burning through their energy and then fading even faster than they brighten. The runaway speed of Comet 3I Atlas has already surpassed all models, indicating that we are witnessing a completely new process that human astronomy has never fully understood. Of course, this doesn't mean Earth is in danger. NASA has confirmed it will stay far away from us, at its closest point still being twice the Earth-Sun distance. So the alert isn't about a collision, it's about understanding, or rather, about we may be watching a time capsule from an alien solar system undergo a cataclysmic transformation right before our eyes. Think carefully about the implications. This object was born around another star, possibly hundreds of light years away. All the matter that constitutes it has never felt the warmth of our sun, nor has it experienced anything that shaped our solar system. And now, for the first time in its history, it has plunged headfirst into the radiation furnace of our inner solar system. The surge in brightness could be the sign of an alien chemical reaction, dormant for billions of years, being awakened. Those ice crystals which remained in a strangely stable state in the deep cold of space might now be experiencing their first awakening since their birth. We might be witnessing the chemical signature of another star system slowly unfolding right before our eyes. And the urgency of time makes this drama all the more thrilling. Comet 3I Atlas is approaching a series of key dates that will determine just how many secrets we can glimpse from this cosmic enigma. October 3rd is its rendezvous with Mars at an incredibly close distance, close enough for the orbiters around Mars to see stunning details we absolutely cannot see from Earth. Then comes the end of October. On October 29th, the comet will reach the apex of its journey, perihelion, the moment of its closest approach to the Sun. However, for us on Earth, the story takes a desperate turn here. Just as Comet 3I Atlas is about to put on its most spectacular performance, its position in the sky draws dangerously close to the blinding glare of the Sun. Starting from early October, it will enter what astronomers call the death zone, a state of solar conjunction. During this period, the Sun's glare will completely overwhelm it, rendering all telescopes on Earth blind. This means the climax of our interstellar visitor's performance will unfold in secret, hidden from all our eyes. We will have to rely entirely on the robotic eyes we have deployed around Mars to witness for us what could be the most spectacular interstellar chemistry experiment in human history. Its ever-increasing brightness already indicates it will not pass by quietly. Current signs suggest this visitor from beyond is becoming extremely agitated by its encounter with the Sun, and may even be brewing a cosmic-scale outburst of unprecedented proportion. But will these earth-shattering secrets be revealed precisely in the few weeks when we are blinded by the Sun? The data from September has already painted a picture of a celestial body undergoing a bizarre transformation. Its brightness has traced an illegal curve, showing it is becoming something entirely different from what it was while traversing the cosmos. The real question is this transformation a normal performance for an alien visitor, or is this something we have never imagined? A completely unprecedented cosmic phenomenon. In the upcoming sections we will delve deeper into why its atmosphere has expanded to an impossible size, why its tail bizarrely points towards the Sun, and what kind of never-before-seen alien chemical reaction its recent unsettling green glow might portend. The mysteries are multiplying at the same frantic pace as its brightness. But first we need to understand exactly what we are dealing with. Because Comet 3I Atlas is far from an ordinary comet. It is only the third confirmed visitor from another star system in human history, and its behavior has already proven that every interstellar guest brings its own set of bizarre rules. Part 2. The appearance of a cosmic ghost. The story of Comet 3I Atlas begins on a desolate mountaintop in Chile. There, a cold robotic telescope tirelessly scans the night sky with superhuman precision. On July 1, 2025, a system named Atlas captured a faint, moving speck of light against the backdrop of the stars. Initially, it was dismissed as just another unremarkable small object, but no one knew this observation would completely rewrite our understanding of interstellar visitors. A celestial body is called an interstellar visitor not just because it comes from outside the solar system, but because it has been mathematically sentenced to death. It can never be bound by our Sun's gravity. Comet 3I Atlas is hurtling along a path known as a hyperbolic orbit. This is a decisive path of no return. Once it swings around our Sun, it will fly outwards forever, never to look back. The verdict of orbital mathematics is cold and unforgiving. This object carries too much energy, so much that our Sun's gravity simply cannot hold on to it. The designation 3I itself tells a legendary story. The I stands for interstellar, and the number 3 is a stark reminder that this is merely the third such object ever confirmed in recorded human history. Its predecessors Oumuamua in 2017 and Borisov in 20, each one left astronomers speechless with their bizarre characteristics that defied easy classification. Now Comet 3I Atlas perfectly continues this family tradition of interstellar oddities. The process of this discovery also reveals just how difficult it is to catch these cosmic ghosts. The Atlas system is part of a global warning network designed to detect potentially Earth-impacting asteroids. It takes multiple images of the same patch of sky in a short period, and then uses algorithms to pick out any moving object. On that July night, Comet 3I Atlas looked like nothing more than a faint streak. It was almost indistinguishable from the thousands of pieces of space junk in our solar system. However, when astronomers looked back at older images, they were shocked to find that this thing had actually been lurking under our noses for several weeks. This delayed discovery is common for interstellar objects. They often masquerade as ordinary asteroids at first, only revealing their cometary features later. Initial assessments showed a faint atmosphere enveloping its core, immediately indicating it was no ordinary rock. Comets form this fuzzy atmosphere or coma when the sun's heat causes the ice within them to sublimate. The appearance of a coma so far from the sun suggested this object contained extremely volatile materials, easily ignited even in the cold outer reaches of the solar system. As news of this discovery spread through the astronomical community, more powerful telescopes around the world began to turn their gaze towards this new interstellar visitor. The Hubble Space Telescope captured high-definition images of it in July. The Very Large Telescope in Chile and other ground-based giants also joined the observation campaign. These follow-up studies revealed a bizarre object far more complex than that initial blurry photograph suggested. Estimates of the size of Comet 3I Atlas remain frustratingly vague, a common challenge when studying distant objects. The latest data from the Hubble telescope can only pin its diameter to a vast range between 0. This range perfectly reflects how difficult it is to see its true form, shrouded by a massive cloud of gas and dust. The uncertainty in its size is critical, as it directly affects all our calculations of its mass density and structural stability. The results of its velocity calculations, however, paint a clearer picture of just how alien this thing is. It is blazing through space at a terrifying speed of about 200,000 kilometers per hour, or 58 kilometers per second. The speed of Comet 3I Atlas makes any local native in the solar system seem like it's crawling in place. For comparison, our Earth orbits the Sun at a steady speed of 30 kilometers per second. As the Sun's gravity continues to pull it closer, the comet's speed will increase even further, potentially reaching a staggering 68 kilometers per second. These speeds completely expose the alien nature of our visit. No object native to our solar system could achieve such an insane velocity without a gravitational slingshot from a large planet. Comet 3I Atlas carries its innate interstellar kinetic energy. This is the imprint shaped by the gravitational fields of countless stars and the rotation of the Milky Way galaxy over millions of years of its journey. Every confirmed interstellar visitor is extremely rare, making any one of them an invaluable treasure to the scientific community. Before 2017, astronomers only had empty theoretical models to guess at the behavior of these cosmic wanderers. Oumuamua, with its bizarre cigar-like shape and mysterious acceleration, shattered everyone's expectation. Borisov looked more like a normal comet, but its chemical composition was completely different from anything in our solar system. Now Comet 3I Atlas adds a third data point to this small group, and early signs indicate it will be just as much of a maverick as its predecessor. Its behavior is challenging all our existing models in a completely new way. Each interstellar visitor seems to come with its own set of physical and chemical rules, suggesting that the formation processes of celestial bodies in the Milky Way are far more diverse and strange than we imagine. The classification process involves more than just confirming its interstellar identity. Astronomers must also figure out if it is an asteroid, a comet, or something entirely different that we've never seen before. The presence of a coma strongly suggests it's like a comet, but only spectral analysis can ultimately reveal its true chemical composition. This is by no means a local comet kicked in from the Oort cloud at the edge of our solar system. Comet 3I Atlas was formed around another star, and everything the materials within it have experienced is drastically different from our solar system. It represents a living sample of a planet formation process that occurred light years away, possibly billions of years ago. Orbital calculations show its path will provide an unprecedented opportunity for observation, especially on October 3rd when it will pass by Mars. This geometric coincidence seems almost prearranged. Just as Earth's telescopes are about to be blinded by the sun, it conveniently flies right in front of the probes we have deployed at Mars. But to understand what we are seeing, we need more than just knowing where it came from and where it's going. The real mystery lies in how it behaves when it encounters the fury of our sun for the first time in its history, and why this behavior differs so greatly and so unsettlingly from our theoretical prediction. Part 3. A calculated disappearance. Time is running out for Comet 3I Atlas, and it is equally pressing for the astronomers racing to understand it before it disappears. The cold mechanics of its orbit have already mapped out a precise route, marking several key dates that will determine just how many secrets we can glimpse from it. October 3, 2025 is the first critical milestone. On this day, Comet 3I Atlas will speed past Mars at a mere distance of 30 million kilometers. On a cosmic scale, this is an extremely close and dangerous encounter, placing the interstellar visitor directly in the crosshairs of the probes we have deployed around Mars. This timing is, you could say, incredibly lucky, and also incredibly frustrating. Just as it gets closest to Mars, offering us the clearest view in history, telescopes on Earth will begin to lose sight of it. Cruel orbital geometry is causing the comet to draw ever closer to the sun in our sky, and an unavoidable observational catastrophe is imminent. By late October, on October 29th, Comet 3I Atlas will reach its Judgment Day perihelion. This position is just inside the average orbit of Mars, subjecting the interstellar visitor to a level of solar radiation it has never experienced in its billion-year journey across the galaxy. And this timing almost perfectly coincides with the period when it is most difficult for us to observe from Earth. The evolution of its speed alone tells a thrilling story. Currently moving at tens of kilometers per second, its speed will peak near perihelion, potentially reaching as high as 68 kilometers per second. To give you a sense of this, our Earth maintains its stable orbit at a speed of about 30 kilometers per second. This means Comet 3I Atlas will be moving at more than twice the speed of our entire planet. These speeds are not just impressive statistics, they reveal the underlying physics governing interstellar motion. The kinetic energy carried by Comet 3I Atlas has been accumulated throughout its journey across countless star systems. Its orbit approaching the Sun happens to lie near the ecliptic plane, the same plane where most of the planets reside. This coincidence facilitates its close encounter with Mars and will allow it to approach Jupiter in 20. This orbital alignment seems almost as if it were meticulously calculated. An object arriving from a random direction is unlikely to conveniently pass close to multiple planets in such a short period. Although it was initially classified as a potentially hazardous object upon discovery, it actually poses no threat to us. Its closest approach to Earth will still be almost twice our distance to the Sun, far outside any possible threat range. NASA's confirmation has allayed public fears, allowing astronomers to focus all their energy on the scientific opportunity. The real challenge lies in the geometry of observation. From early October to early November, Comet 3I Atlas will enter a state of solar conjunction, where it is too close to the Sun in the sky for any practical observation. For most of this critical period, its angular separation from the Sun will be less than 30 degrees. Imagine trying to spot a faint firefly next to a giant searchlight, and you'll understand the desperation of this observation. Even the world's most powerful telescopes cannot separate its faint light from the overwhelming glare of the Sun. This natural limitation of Earth-based astronomy means the comet's most active and spectacular period will likely escape human observation to a large extent. The timing of the conjunction creates a fundamental irony in this encounter. Just as the sun's heat reaches its maximum intensity and the comet may undergo its most drastic transformations, the astronomical community on Earth will be effectively blinded. The peak of outgassing, possible fragmentation and maximum tail development could all occur during those weeks when ground-based telescopes are completely inoperable. This observational gap makes the spacecraft we have deployed throughout the solar system, especially those orbiting Mars, exceptionally important. The European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter, among others, suddenly find themselves cast as humanity's primary observers to witness one of the most important astronomical events of the century. The timeline after perihelion brings both hope and a harsh reality. Assuming it survives its encounter with the Sun intact, our observations from Earth should resume in November or early December, as it moves farther away. However, by that time the comet will likely have dimmed rapidly, having expended a vast amount of energy during its unobserved peak heating period. Brightest predictions suggest that even at its brightest, it will remain a telescopic object for us on Earth. While the lack of a spectacular naked-eye sight might disappoint the public, it does not diminish the scientific value of this unprecedented interstellar encounter. The velocity profile reveals another key aspect of its timeline. As it approaches perihelion, its speed continuously increases under the Sun's gravity. However, after the closest point, the same gravity begins to slow it down. This change in velocity affects the duration of the peak heating period and the time window available for our Mars probes to observe. Looking ahead, orbital calculations show it will approach Jupiter in March 20. Although this encounter will be at a much greater distance, it may provide additional observational opportunities. This timeline creates a narrow window of opportunity that astronomy has never faced before. Unlike comets that return periodically, Comet 3i Atlas gives us only one chance to understand an object from another star. All the challenges, timing, and opportunities must align perfectly for us to extract the maximum scientific value from this cosmic visitor. As we approach the critical month of October, the question is not only what it will reveal about itself, but whether our observational capabilities are sufficient to capture those fleeting revelations. The mathematics of orbital mechanics have set the schedule, and this schedule waits for no one. Part 4, An Impossible Structure. The most astonishing discovery about Comet 3i is not its interstellar origin, or its bizarre orbit. It is the atmosphere it has created around itself, on a scale that is simply impossibly large. In September 2025, NASA's FARIX telescope detected a phenomenon that overturned all of astronomers' models. A massive cloud of carbon dioxide, extending 308,000 kilometers, was expanding wildly outwards from the comet's nucleus. To understand just how exaggerated this size is, you can imagine that this ghostly atmosphere has stretched to about half the diameter of our Sun. The coma of Comet 3i Atlas has grown large enough to easily contain the entire orbit of Mercury, creating a gigantic bubble of gas and dust that dwarfs any comet from our solar system. This is not just unusual, it is unprecedented in the history of cometary science. A coma forms when solar radiation heats the ices locked within a comet's nucleus. This causes them to sublimate, turning directly from a solid to a gas, without passing through a liquid state. You can think of it as a cosmic snowball steaming in the sunlight, but this analogy completely fails to capture the violence of the process. As materials frozen for billions of years explosively transform into gas, they carry dust and debris outwards, forming an expanding atmosphere that can grow to monstrous proportions. And the composition of the coma of Comet 3i Atlas tells a story of formation under bizarre conditions, entirely different from those in our solar system. Its primary component is carbon dioxide, not water vapor, which indicates it was born in a region where it was easier for CO2 to freeze than water. This CO2-rich environment hints at the unique chemical conditions present at its birth. Most comets in our solar system have water as their main volatile component. The reversal of this ratio observed in Comet 3I suggests that the temperature and pressure during its formation were completely different from any conditions experienced by native objects in our solar system. But the composition of the coma is not its only unusual feature. Images from the Hubble Space Telescope have revealed a structure that challenges the fundamental assumptions of cometary behavior. Instead of a classic tail streaming away from the Sun, Comet 3I displays what astronomers call an anti-tail, a plume of material that appears to point directly towards the Sun. This sunward-pointing structure is a huge puzzle that has researchers working around the clock. Traditional comet physics dictates that the solar wind should push gas and dust away from the Sun, forming the familiar tail we know. However, Comet 3I seems to be openly violating this fundamental principle, ejecting material in the complete opposite direction of the textbooks. Hubble's observations captured what mission scientists described as a forward-facing glow. This is a fan-shaped structure extending from the nucleus towards the Sun, rather than away from it. Subsequent imaging has shown that this unusual geometry persists, and is continually evolving. This indicates that the anti-tail is a stable feature, not just a temporary anomaly. The physics behind the formation of an anti-tail are far more complex than we might think. One theory suggests that if large enough dust particles are ejected at a very high initial velocity, they can resist the push of sunlight and maintain an orbit that appears to head towards the Sun. Additionally, projection effects can make material moving in three-dimensional space appear to point towards the Sun from our specific vantage point. However, theoretical models struggle to explain the persistence and prominence of the anti-tail of Comet 3I. Its structure seems too well defined and lasts too long to be a simple projection effect. Recent analysis suggests that the anti-tail may be caused by an unusual rotation state or surface properties unique to interstellar objects. A slowly rotating nucleus could maintain a huge temperature difference between its sun-facing and anti-sun-facing sides, thereby concentrating gas eruptions in a specific direction. Alternatively, the surface composition of Comet 3I may contain materials we've never seen before, which react to solar heating in ways completely unfamiliar to scientists who study local comets. The expansion rate of the coma adds another layer of strangeness to this mystery. Spectroscopic observations show that the gas velocity within its atmosphere exceeds that of any comet at a similar distance. This enhanced gas eruption could be caused by the release of supervolatile compounds, which remain stable only in the extreme cold of interstellar space, and sublimate violently upon their first exposure to solar heat. Temperature measurements of the coma have revealed even more anomalies. Infrared observations recorded temperatures that suggest the presence of an unknown heating mechanism beyond simple solar heating. Possible explanations include violent chemical reactions between previously separated compounds, or the instantaneous release of energy stored in exotic ice crystal structures formed under interstellar conditions. The three-dimensional structure of the coma shows extreme asymmetry, pointing to uneven outgassing from the nucleus's surface. Unlike the relatively symmetrical comas we are familiar with, Comet 3I exhibits jets and fan-like structures of material erupting from specific regions of its core. These jets suggest that the nucleus's surface contains discrete, volatile-rich areas, possibly exposed by impacts or thermal cycling during its long interstellar journey. Dust analysis within the coma has revealed a particle size distribution completely different from that of comets in our solar system. The large quantity of big particles required to form that anti-tail suggests that either Comet 3I formed with a different dust-to-ice ratio than local comets, or its dust particles underwent some unknown alteration process during their interstellar transit. As it continues to approach perihelion, its atmosphere will continue to grow and evolve, potentially reaching even more exaggerated sizes. Modeling its future evolution is facing unprecedented challenge. The unusual composition, the geometry of the anti-tail and the enhanced outgassing rate all demand a thorough revision of standard cometary physics models. As observations continue to reveal unexpected behavior, researchers are essentially developing new theoretical frameworks in real time. The implications extend beyond Comet 3I Atlas itself. If interstellar comets commonly exhibit such unusual features, it suggests that our understanding of cometary physics, based primarily on native solar system objects, may only be the tip of the iceberg. Each interstellar visitor may force us to revise our fundamental assumptions about how these objects form and evolve. As it approaches its key encounters with Mars and the Sun, the continued expansion and structural evolution of its coma will provide a critical test for competing theoretical models. The only question is whether the most dramatic changes will occur within the observational blind spot of our Earth-based telescopes. But the evolution of the coma is just one aspect of its transformation. The most striking visual change occurred in mid-September, when the entire comet began to glow with an eerie green light, heralding a chemical reaction unlike any previously observed in an interstellar visitor. Part 5. The eerie green glow. A faint ghostly green glow. In mid-September 2025, Comet 3I Atlas did something that sent shockwaves through the astronomical community. It turned green, not a faint, barely perceptible green, but a vibrant emerald green glow that transformed the interstellar visitor from a pale speck of light into something that looked almost alive in the darkness. This color change was not immediately visible to the casual observer. It was still too dim to be seen with the naked eye, but sensitive cameras on telescopes around the world began to capture images showing a distinct green hue around the comet's nucleus. The transformation became particularly evident in photos taken during the lunar eclipse on September 14, when the moon's shadow provided a darker sky, enhancing the contrast of the comet's newfound radiance. This green light tells a bizarre story written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet light from the sun, their electrons jump to higher energy levels. When these electrons fall back down, they emit light at a specific wavelength, which our eyes perceive as a distinct color. In the case of Comet 3I Atlas, the green light most likely originates from diatomic carbon. That is, a molecule made of two carbon atoms bonded together. In space, diatomic carbon acts like a molecular neon sign. When excited by the sun's ultraviolet radiation, it emits light with a wavelength of around 516 nanometers. Producing that characteristic green glow. This process, known as fluorescence, transforms invisible solar energy into visible light. But here the story becomes perplexing. Early spectroscopic observations of Comet 3I Atlas showed relatively little evidence of carbon-based compounds. Initial chemical analysis suggested its composition was dominated by carbon dioxide and water vapor. The glaring contradiction between the intense green light observed and the measured chemical composition has sent researchers scrambling to figure out what is truly happening in the comet's expanding atmosphere. One possibility is that its outgassing behavior has undergone a phased transition. As it moved closer to the Sun and crossed the 2 astronomical unit threshold in early September, the increased solar heat may have begun to sublimate previously inaccessible, carbon-rich materials within the nucleus. These materials, locked deep inside the comet during its long interstellar journey, might now be experiencing solar radiation for the very first time. The timing of the green transformation coincides suspiciously well with the period of rapid brightening observed in mid-September. This suggests that the same physical process that caused the unexpected brightness surge also triggered the chemical reactions producing the green emission. Another explanation involves more complex chemical processes than simple fluorescence. Comets can contain dozens of different carbon-bearing molecules. The prominent green light could be the result of combined emissions from a mixture of substances, or it could come from a carbon-bearing molecule unique to the interstellar medium that we have never seen before. The evolution of the green light provides additional clues to the underlying chemical processes. Observations show that the intensity and distribution of the green color within the coma are variable, with some regions appearing greener than others, indicating that carbon-bearing molecules are not uniformly distributed in the expanding gas cloud. This uneven distribution could be due to discrete outgassing events, where jets of material erupting from specific locations on the nucleus carry different chemical composition. Alternatively, this variation might reflect chemical processing within the coma itself, where solar ultraviolet light breaks down complex organic molecules into simpler fragments. The green emission also provides a diagnostic tool for understanding the physical conditions within the coma. By measuring how the green light changes over time and with distance, researchers can map the three-dimensional structure of the carbon-bearing gas in its atmosphere. The appearance of green on Comet 3I Pliss adds another data point to the growing list of differences between interstellar visitors and native solar system objects. Oumuamua showed no cometary activity and therefore no color change. Borisov, on the other hand, exhibited a more traditional color, dominated by scattered sunlight. Comet 3I Pliss is the first interstellar comet to develop a classic green coma. However, the specific wavelength and intensity of its green emission might differ subtly from familiar comets, which could reveal a chemical composition unique to objects formed in other star systems. The timing of the color change adds further observational urgency. As it approaches solar conjunction and becomes unobservable from Earth in early October, its green emission could continue to evolve or even disappear entirely. The peak intensity of molecular fluorescence typically occurs near perihelion, when solar heating is at its maximum, but this critical period will be largely hidden from Earth-based telescopes. Follow-up spectroscopic observations are attempting to identify the specific molecules causing the green emission, but as astronomers race against the clock to characterize its emission signature before losing the target, every clear night has become precious. The green glow transformation is not just a visually striking development, it is direct proof that Comet 3I Pliss is undergoing fundamental chemical changes as it encounters our sun's radiation. The molecules now fluorescing in its coma have likely remained chemically inert for millions of years, preserved in a state of frozen silence as the object journeyed through the interstellar medium. Now, for the first time since its formation, Comet 3I Pliss is literally lighting up, as solar energy activates chemical processes that have been dormant since the comet was born around another star. The green glow marks the awakening of alien chemistry. It is the first stirrings of molecular activity in material formed under conditions that may be unlike any in our solar system. But observing this awakening presents immense challenges that will soon force researchers to rely on robotic eyes deployed throughout the solar system to continue monitoring our transformed interstellar visitor. Part 6. The Desperate Race Against Time. The universe has an almost cruel sense of humor when it comes to Comet 3I. Just as this interstellar visitor begins to reveal its most fascinating secrets, the cold laws of orbital mechanics conspire to snatch it from our view at the most critical moment of its journey. Even the most sophisticated telescopes built by humanity face the same fundamental limitation as the average person. You can never observe something hidden behind the sun. As Comet 3I Pliss continues its death march toward the sun, its position in the sky inevitably draws closer to the all-consuming glare of our star. The James Webb Space Telescope managed to seize an extremely brief window on August 6 to conduct spectroscopic observations, providing crucial data on its chemical composition. These observations represent possibly the most detailed chemical analysis ever performed on an interstellar object, but they occurred before the dramatic transformation in September that changed everything. The Hubble Space Telescope also contributed its own observations on July 21, capturing the bizarre sunward pointing plume structure. However, since August, new high-resolution images from these top-tier observatories have become increasingly rare. The very telescopes most capable of unraveling the mystery are also the most susceptible to interference from the sun. Ground-based observatories face their own set of complex problems. Different telescopes using different equipment do not always produce consistent brightness measurement. This inconsistency is not uncommon in astronomy, but it adds another layer of fog to this already bizarre puzzle. Comet observation databases attempt to reconcile these differences by collecting reports from observers worldwide. Throughout September, the data clearly showed that the brightness trend of Comet 3I Pliss was consistently higher than expected. But the clutter in individual measurements also reflects the immense challenges observers face when trying to track a rapidly changing and completely unpredictable object. Amateur astronomers have contributed valuable long-term monitoring data. However, their measurements also face additional uncertainties from the atmosphere, light pollution, and equipment. The final result is a scattered collection of observations that together paint a highly unusual picture, yet each data point is fraught with uncertainty. The elongation or the angular separation between it and the Sun as seen from Earth is the fundamental factor limiting all observation. When this angle drops below 30 degrees, even the most powerful telescopes struggle to distinguish the comet's faint light from the sunlight scattered by our atmosphere. Professional observatories are usually forced to give up when the angle falls below 20 degrees, and this timeline is creating a death countdown that no human technology can extend. In early October, its elongation drops below 30 degrees, marking the beginning of severe observational difficulty. By mid-October, the angle shrinks to less than 20 degrees, effectively signaling the end of routine observations from the Earth's surface. This period of invisibility will last until early November, precisely covering the critical few weeks when solar heating reaches its maximum intensity. The irony is palpable. We are trying to observe a cosmic firefly hovering next to a searchlight with instruments designed to detect the light from the most distant galaxy. In theory, space-based observatories are better equipped to handle solar interference, but they too face their own limitations. Top-tier instruments like Hubble and Webb have built-in protection systems that prevent them from pointing too close to the Sun. These safety systems, designed to protect the instruments, are precisely what create the observational gap when the observations are needed most. The timing of the solar conjunction could not be worse for understanding its peak activity. Theoretical models predict that the greatest gas eruptions, possible fragmentation events, and the most spectacular tail development should all occur around its perihelion in late October, and these very phenomena, which could best reveal its true identity, will be largely hidden from human observation. As observing conditions deteriorate, coordination among global observatories becomes crucial. Facilities located in different corners of the world must work together to maximize the extremely limited observing window each night. Weather adds another layer of uncertainty to ground-based observation. Unlike periodic comets whose returns can be predicted, Comet 3II Tellus offers only one chance, making every clear night precious and irreplaceable. As ground-based astronomy gradually reaches its limits in observing it, the burden of continuous monitoring shifts to our robotic eyes deployed throughout the solar system. Spacecraft designed for entirely different missions, orbiting Mars, suddenly find themselves as humanity's primary observers for one of the most important astronomical events of the century. Part 7: The growing unease of scientists. Behind the rigorous language of scientific papers, a sentiment bordering on excitement, and yes, alarm, is spreading through the global community of comet researchers. The behavior of Comet 3II Tellus is completely off-script from the playbook written by decades of cometary science, and astronomers are beginning to admit they might be witnessing something unprecedented. The brightness trends recorded by observers worldwide are far from being mere statistical noise or measurement error. Multiple independent tracking systems all show the same unsettling pattern. The brightness of Comet 3II Tellus consistently and systematically exceeds the predictions of all standard models. The magnitude of this deviation is well beyond what can typically be attributed to observational uncertainty. A comet scientist named Matthew Knight pointed out that the rapid brightening event observed in mid-September challenges fundamental assumptions about the mechanisms of material release in comets. He proposed that the speed of this change suggests a process operating on a much faster timescale than the gradual heating models we typically use to predict cometary behavior. This scientific uncertainty has fostered a unique kind of excitement among researchers. They recognize that they may be observing a phenomenon that requires a completely new theoretical framework to understand. The bizarre sunward-pointing plume structure has triggered another category of scientific puzzle. The phenomenon of an anti-tail is not unheard of in cometary science, but the persistence and prominence of the forward-facing jet of Comet 3II Tellus push the limits of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios: unusual dust particles, non-uniform nucleus rotation, strange chemical mixtures to account for this textbook-defying behavior. One point of agreement among everyone in the field is that Comet 3II Tellus exhibits an enhanced level of activity compared to a typical comet at a similar distance. Its carbon dioxide-dominated coma, extending to unprecedented distances, indicates a gas production rate that significantly surpasses standard predictions. This is not a minor deviation from theory. It is a massive departure that demands an explanation. However, the scientific community is also grappling with what is known as outburst bias. This is the tendency for comets to experience brief periods of enhanced activity, which can create the illusion of sustained abnormality. The question plaguing observations is whether the September brightening represents a true departure from normal behavior, or is merely a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes even more acute when considering the impending observational gap. The most critical period for understanding its true nature will be largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this time, researchers may never fully understand what they witnessed in September. Kelly Holt of the European Southern Observatory expressed the frustration felt by many researchers. The very moment Comet 3II Tellus might reveal its most important secrets coincides with the period when Earth's astronomical observation capabilities are at their weakest. She called this timing a cosmic conspiracy against scientific understanding. The debate has extended to fundamental questions about what it represents as a physical entity. Its chemical composition shows a ratio of carbon dioxide to water that is completely different from solar system comets. This difference could indicate formation conditions drastically different from our local environment. Alternatively, it might reflect some unknown chemical processing that occurred during its millions of years of interstellar travel. The excitement building around Comet 3II Tellus reflects a fundamental aspect of scientific discovery. It is the recognition that nature continuously produces phenomena more complex and surprising than human theories can predict. As October approaches and ground-based observations become increasingly difficult, astronomers are pinning their hopes on the spacecraft we have deployed throughout the solar system, hoping they can capture the revelations that ground-based telescopes will be forced to miss. Part 8. Mars, the golden front row seat. While we on Earth anticipate losing sight of Comet 3II Tellus in the sun's glare, another world is preparing to watch one of the most significant astronomical events of recent times from a front row seat. On October 3, 2025, Mars will host the closest encounter between humanity and an interstellar visitor, providing an unprecedented opportunity for our spacecraft orbiting the red planet. This geometric alignment could not be more fortunate. As Comet 3II Tellus skims past Mars at a distance of about 30 million kilometers, several spacecraft we have deployed there will have the chance to turn their instruments toward the cosmic visitor. This timing falls just days before ground-based tracking becomes impossible, thus enabling a critical handover from ground-based to space-based monitoring. The European Space Agency's Mars Express orbiter carries a high-resolution stereo camera. Though designed for planetary geology, its sensitivity and resolution might be sufficient to capture detailed images of the comet's nucleus and inner coma structure. Colin Wilson, project scientist for the ExoMars Trace Gas Orbiter, confirmed that mission planners are evaluating opportunities for the orbiter's instruments to observe the interstellar visitor. These instruments, designed to study the composition of the Martian atmosphere, might be able to detect chemical signatures within its expanding coma. NASA's Mars Reconnaissance Orbiter offers perhaps the most intriguing possibility. Its high-resolution imaging science experiment camera, or HiRISE, can typically capture details on the Martian surface smaller than 1 meter from orbit. Although Comet 3II Tellus will pass by at a much greater distance, the extraordinary resolution of HiRISE might be able to resolve structural details of the nucleus that are absolutely impossible to see with Earth's telescope. However, these observational opportunities come with significant technical challenges. All Mars orbiters were designed to study Mars itself, not to track a fast-moving object against the backdrop of the stars. These spacecraft, developed to observe a huge nearby planet, must be reconfigured to track a small distant target, moving at interstellar speed. Signal strength is the most fundamental limitation. Even at its closest approach to Mars, Comet 3I88 Atlas will appear extremely faint to spacecraft designed for planetary observation. Dr. Wilson acknowledged these limitations, noting that while Mars-based observations are theoretically possible, the actual scientific return depends on a multitude of factors. The advantage of Mars-based observation is not just its proximity. During the flyby on October 3rd, the viewing geometry from Mars will offer a unique perspective, unavailable from Earth. The solar phase angle, the angle between the Sun, the comet and the observer, will differ significantly between the views from Mars and Earth, which could reveal structural details invisible to ground-based telescopes. The interaction of Comet 3I88 Atlas with the solar wind is another area where Mars orbiters could contribute unique observations. These interactions, through changes in its magnetic field and electrical properties, could reveal information about the comet's internal structure and composition. The coordination efforts for the Mars flyby observations involve unprecedented collaboration between missions, designed for completely different scientific objectives. Mars Express, originally slated for surface geology studies, finds itself repurposed as an interstellar object observatory. Time constraints add complexity to the observation planning. Inserting observations of Comet 3I88 Atlas into these pre-scheduled timelines requires careful coordination. The challenge of data transmission is immense. Images and spectral data from it must compete for limited communication bandwidth with regular planetary science data. If the Mars-based observations succeed, their scientific value for understanding Comet 3I88 Atlas could be transformative. High-resolution imaging might be able to resolve the size and shape of the nucleus with unprecedented accuracy. Spectroscopic observations might detect molecular species invisible from Earth's telescopes, revealing its true chemical composition. Structural details of the coma and tail, especially that unusual sunward pointing plume that has puzzled researchers, might become clearer from Mars's unique vantage point. The different perspective might reveal whether the anti-tail structure is caused by a genuine sunward ejection of material, or is a projection effect. Realism requires us to have reasonable expectations for what the Mars orbiters can achieve. Even under the best conditions, the scientific return from these observations may be just a small number of images and spectra. These instruments were never designed for this type of observation, and their capabilities may be insufficient to answer all the fundamental questions about it. Success or failure depends on variables beyond human control. If it undergoes another brightening event before October 3rd, it might become detectable by the Mars orbiters. Conversely, if the comet dims, even the most optimistic observation plans may yield no useful data. The Mars flyby represents humanity's best and last chance to maintain surveillance on this interstellar visitor during the critical weeks when Earth's telescopes lose sight of it. As our astronomy prepares for the mandatory silence that will last until early November, the robotic eyes orbiting Mars offer our only hope of witnessing the most spectacular phase of its encounter with our solar system. Regardless of the success of these observations, they mark a new chapter in humanity's study of visitors from other star systems. Part 9. The Cosmic Scale Disappearing Act. The mathematics of celestial mechanics are completely indifferent to human curiosity. As October progresses and Comet 3I88 Atlas continues its relentless journey towards the Sun, the geometric reality of orbital motion conspires to snatch our interstellar visitor away at the precise moment it might reveal its deepest secret. The solar conjunction turns one of the most important astronomical events of recent times into a cosmic scale disappearing act. The timeline unfolds with relentless precision. In early October, its elongation drops below 30. This is the threshold where ground-based telescopes begin to encounter serious observational difficulties. The atmospheric scattering of sunlight creates a bright sky background that drowns out the faint signal of our interstellar visitor. By mid-October, the elongation shrinks to less than 20 degrees, effectively ending routine observations from the Earth's surface. The comet does not disappear suddenly, it fades gradually into the sun's glare, like a star at sunrise, until observation becomes impossible. This gradual transition makes it difficult to pinpoint precisely when Earth completely loses sight of it. But the practical result is the same. Our primary window for peering into the comet's behavior closes just as solar heating approaches its maximum intensity. The conjunction period will last until early November, covering a period of 4 to 5 weeks during which it is effectively invisible to human monitoring. This is not just an inconvenient observational gap, it represents a complete loss of our ability to monitor the comet at the very time we predict it should be most active. Peak gas eruption, maximum tail development, possible fragmentation events, and other dramatic phenomena are all likely to occur beyond the sight of humanity. This cruel irony becomes even more apparent when we consider its recent behavior. The rapid brightening, the unusual anti-tail structure, and the unique green color observed in September all suggest this object is undergoing fundamental changes. Logically, these transformations should intensify as solar heating increases, potentially reaching spectacular levels around its perihelion in late October. However, perihelion occurs almost exactly at the midpoint of the conjunction period, when it appears closest to the Sun in Earth's sky, and observation becomes most impossible. This timing could not be worse for understanding what this interstellar visitor truly becomes when subjected to maximum solar influence. It's as if the universe deliberately scheduled the best part of the show to happen behind a drawn curtain. The physics behind the conjunction phenomenon involves no conspiracy against scientific discovery, but merely the geometric consequences of observing from a planet that orbits the same star as our target object. When ground-based observations resume in November or early December, Comet 3I Tellus will likely be a very different object from the one astronomers studied in September. It may have become brighter, perhaps even developing spectacular tail structure. Alternatively, it may have dimmed significantly if its energy was depleted during its unobserved perihelion passage. More dramatically, it might have fragmented into multiple pieces at its closest approach to the Sun. It's not uncommon for comets to break apart near perihelion. If fragmentation occurs during the conjunction, observers will face the daunting task of identifying and tracking multiple objects when they become visible again. Resuming observations in late November or December will require careful planning and coordination among global observers. It will emerge from the conjunction in a different region of the sky, requiring telescopes to relocate and capture it after weeks of invisibility. The object's brightness, position and appearance may have changed enough to complicate identification and tracking efforts. The conjunction period is a reminder that despite centuries of technological advancement, astronomy still has its fundamental limitations. As Comet 3I Tellus disappears into the Sun's glare, the astronomical community prepares to enter a period of speculation and theoretical modeling, based on incomplete data. The question is not whether the comet will change during its hidden journey, but whether those changes can be understood when observations resume, or if the gap from the conjunction will leave a permanent mystery about what happened to this interstellar visitor during the most critical phase of its encounter with us. Part 110, The Hidden Judgment Day. Deep within the blinding glare of the Sun that incapacitates our telescopes, Comet 3I Tellus is preparing to meet its destiny. On October 29, 2025, this interstellar wanderer will reach perihelion, its closest position to the Sun. Hidden from human observation, the comet will experience a level of solar radiation unprecedented in its millions of years of interstellar travel, potentially undergoing transformations that could redefine our understanding of interstellar objects. The evolution of its velocity alone tells a story of cosmic violence. Currently hurtling at tens of kilometers per second, It will reach its maximum speed near perihelion, potentially hitting 68 kilometers per second. To appreciate this extraordinary speed, consider that Earth maintains its stable orbit at about 30 kilometers per second. Comet 3I Tellus will be moving at more than twice the speed of our entire planet. Physics predicts that perihelion will trigger the most dramatic phase of its solar system encounter. As solar heating reaches its maximum intensity, the temperature of the nucleus will skyrocket, potentially activating volatile compounds that remain stable throughout its interstellar voyage. Water ice, carbon dioxide, carbon monoxide and more exotic frozen gases may all begin to sublimate simultaneously, causing an explosive expansion of the coma that could dwarf the size observed in September. The increased gas eruption will likely produce spectacular dust jets erupting from the nucleus's surface. The sunward-pointing anti-tail that has puzzled observers might intensify dramatically, or entirely new tail structures could appear as different compounds begin to contribute to the coma for the first time. Theoretical models suggest its carbon dioxide-rich composition could lead to perihelion behavior completely different from that of typical solar system comets. This enhanced activity might manifest as rapid changes in brightness, coma size and tail structure, which could occur over hours rather than the usual days or weeks. The possibility of fragmentation looms over the perihelion predictions like a shadow of uncertainty. Comets are among the most fragile objects in the solar system. The thermal stress caused by intense solar heating, combined with the mechanical forces from explosive gas eruptions, can easily tear a nucleus apart. A fragmentation event can unfold with dramatic suddenness. A comet that appears stable on its approach to perihelion could break into multiple pieces within a matter of hours. If Comet 3I Tellus fragments, we will face the complex task of identifying and tracking multiple objects when observations resume in November. However, fragmentation is not inevitable. Its structural integrity depends on a variety of factors. Interstellar objects may possess significantly different structural properties from solar system comets, which could make them either more or less susceptible to thermal disruption. If it survives perihelion intact, the post-perihelion period should reveal an object thoroughly transformed by its encounter with intense solar radiation. The coma might have expanded to even greater dimensions. New chemical species, liberated from the subsurface by deep heating, might appear in spectroscopic observations for the first time. More complex color changes beyond the green emission already observed could emerge. The anti-tail phenomenon that has become its signature could change dramatically near perihelion. Enhanced dust production might create multiple tail structures pointing in different directions. The resulting geometry could provide crucial information about the nucleus's rotation rate, surface composition and internal structure. The perihelion passage represents the climax of its solar system encounter. It is the moment when billions of years of interstellar evolution meet the intense radiation environment around our star. Whether this encounter produces a spectacular cosmic fireworks display or a quiet structural transformation hidden within an expanding coma, perihelion will fundamentally alter Comet 3. The question that will haunt astronomers throughout the conjunction period is whether it will emerge from its hidden perihelion passage, still recognizable as the same object that captivated observers in September, or as something completely changed by its encounter with our sun's most intense radiation. The answer lies hidden in the sun's glare, waiting for the patient geometry of orbital mechanics to reveal the outcome of perihelion. Part 11. The Gathering of Interstellar Mavericks. To understand the significance of Comet 3I Tellus and its bizarre behavior, we must look back at the brief but revolutionary history of confirmed interstellar visitors. Before our current guest, only 2 objects had been definitively identified as originating from outside our solar system, and each, in its own unique way, rewrote the astronomy textbooks. The story they tell together is one of cosmic diversity, challenging every assumption we had about how these wandering messengers from other star systems should behave. Oumuamua was the first to arrive, discovered in October. Initially classified as an asteroid due to its lack of a visible coma, it quickly proved that interstellar objects do not conform to earthly expectations. Its highly elongated, cigar-like shape was unlike any asteroid or comet previously observed in our solar system. Even more perplexing, Oumuamua exhibited a mysterious non-gravitational acceleration as it moved away from the Sun, speeding up in a way that could not be explained by gravity alone. This mysterious acceleration sparked a fierce debate that continues to this day. Was it hidden outgassing, solar radiation pressure acting on an unusually shaped object, or something more exotic, pushing the boundaries of conventional physics? Iva Borisov, discovered in August 2019, presented a completely different personality. Unlike the mysterious behavior of its predecessor, Borisov was refreshingly normal at first glance. It was a classic comet, with a fuzzy coma and a developing tail structure. However, detailed analysis revealed that Borisov's apparent normalcy masked a chemical composition unlike any native material in our solar system. Spectroscopic observations showed a significantly higher concentration of carbon monoxide than in local comets, suggesting it formed in a protoplanetary disk entirely different from our own solar nebula. These subtle but significant chemical differences provided the first direct proof that comets produced in other star systems reflect the unique composition of their formation environments. Now Comet 3I Tellus enters this exclusive club, with characteristics that dwarf both of its predecessors. Its carbon dioxide-rich coma represents the most extreme compositional deviation from the solar system standard observed in an interstellar visitor to date. Its sunward-pointing anti-tail structure has no precedent in previous interstellar object observation. Oumuamua had no tail structure, while Borisov displayed a traditional tail streaming away from the Sun. The geometry created by Comet 3I Tellus challenges the fundamental principles of cometary physics understood through centuries of observation. The rapid brightening trend recorded in September 2025 adds another unique feature to its growing list of anomalies. Neither Oumuamua nor Borisov exhibited such dramatic short-term brightness variations, suggesting that the processes at work in Comet 3I Tellus operate on a much faster timescale than in previously studied interstellar objects. Size comparisons reveal an interesting pattern among the population of interstellar visitors. Oumuamua's size was estimated to be significantly larger than a typical asteroid. The nucleus diameter of Borisov fell within the normal range for solar system comets. The size estimates for Comet 3I Tellus reflect the immense uncertainty surrounding its basic property. Hubble observations suggest a nucleus diameter between 0.32 and 5.6 kilometers, a huge range stemming from the difficulty of separating the nucleus from its abnormally vast coma. The orbital characteristics of each interstellar visitor also tell their own story about galactic dynamics. Oumuamua's hyperbolic excess velocity was measured at about 26 km per second. Borisov's hyperbolic excess velocity was about 32 km per second, and Comet 3I Tellus carries the highest hyperbolic excess velocity measured for an interstellar object to date, estimated at about 39 km per second. This extremely high speed suggests it was either formed around a particularly massive star, or was accelerated through multiple gravitational encounters during its journey across the galaxy. A statistical analysis of these three confirmed interstellar objects suggests that each represents a different type of small body formation process, indicating a huge diversity in the ways other star systems produce and eject objects. Each new interstellar visitor expands the range of possible behaviors and compositions. The unique characteristics of Comet 3I Tellus suggest that the diversity of interstellar objects includes phenomena not yet imagined by theoretical models based on solar system experience. As it continues its hidden passage to perihelion, astronomers can only speculate whether its post-conjunction appearance will add new entries to the growing catalogue of interstellar oddities. The pattern established by Oumuamua and Borisov suggests that Comet 3I Tellus will continue to surprise researchers with behavior that challenges fundamental assumptions of small body physics. The lesson from all three interstellar visitors is that the galaxy produces small bodies through processes far more diverse and complex than those operating in our local solar system. Each object carries the chemical and physical signatures of formation in an environment drastically different from our cosmic home, providing direct samples of planetary system evolution occurring throughout the galaxy. Part 12. The fierce scientific debate. The scientific community's response to Comet 3I Anomalous is like a detective story where the key evidence remains under lock and key, forcing researchers to build theories from incomplete clues. Multiple competing hypotheses attempt to explain the comet's unusual behavior, but each explanation raises new questions. The debate over the nucleus size and shape illustrates the fundamental challenges researchers face. Hubble observations have narrowed the size estimate to a diameter between 0.32 and 5.6 kilometers. But this wide range reflects the difficulty of separating the solid nucleus from its vast coma. This uncertainty is critical because it directly affects all calculations of mass, density, and structural stability. Different measurement techniques have yielded conflicting results. Thermal models from infrared observations suggest a smaller, highly reflective nucleus. Visible light analysis, on the other hand, points to a larger, darker nucleus. This discrepancy could be due to variations in surface composition, or a fundamental misunderstanding of how it responds to solar heating. Compositional analysis also faces its own set of contradictions. Spectroscopic analysis from the Webb telescope clearly identifies carbon dioxide as the primary volatile. However, the dominance of carbon dioxide creates theoretical problems for explaining other observed features. The green color that appeared in September typically indicates the emission of diatomic carbon, but a CO2-rich outgassing does not naturally produce the carbon-bearing molecules that lead to green fluorescence, suggesting either that the spectral analysis missed important chemical components or that the green color is caused by a more complex process than we imagine. The anti-tail structure is perhaps the most perplexing observational puzzle. Traditional comet physics dictates that solar radiation pressure should push gas and dust away from the sun. Comet 3I Anomalous appears to violate this fundamental principle. Recent theoretical analysis proposes that the anti-tail is caused by an unusual dust particle size combined with a specific ejection geometry from the nucleus surface. Their models suggest that large dust particles ejected towards the sun with sufficient initial velocity can overcome solar radiation pressure. However, competing models invoke different physical mechanisms. Some researchers propose that electromagnetic effects could redirect material in unexpected directions. Others argue that its rotation state creates temperature asymmetries that concentrate gas eruptions in specific directions. Despite months of observational attempts, its rotation period remains unknown. Light curve analysis, which measures changes in brightness, has failed to reveal a clear periodic signal. The lack of a detectable rotation signature could indicate that its rotation is very slow, or that its complexity masks a simple periodic variation. The brightness evolution recorded in September also presents its own interpretive challenges. Multiple observation networks have confirmed that it became much brighter than theoretical predictions, but the magnitude of this deviation is still under debate. Some observers reported brightness increases equivalent to several magnitudes, while others suggested a more modest increase. These discrepancies are partly due to the difficulty of the measurements. More fundamentally, the lack of baseline observations complicates the analysis of brightness trends. Unlike periodic comets observed over multiple returns, it is a single opportunity target with no historical data for comparison. Origin studies have attempted to trace its trajectory back through the galaxy to identify its likely birthplace. Current kinematic analysis suggests it originated from somewhere within the thin disk of the Milky Way. However, uncertainties in the measured position and velocity propagate backward in time, creating increasingly large error ellipses that contain multiple possible source regions. Structural stability is another area of intense debate. The vast coma and anti-tail structure indicate violent outgassing, which could suggest a nucleus rich in volatiles or one undergoing structural disintegration. Some researchers propose that it is a loosely bound collection of smaller bodies, a rubble pile that could fragment under thermal stress. An alternative model views it as a single solid body with unusual surface properties or internal structure. This distinction is crucial for predicting its behavior near perihelion, The observational gap during the solar conjunction adds an extra layer of uncertainty to which theoretical model best explains its behavior. The most critical test of the competing hypotheses will be largely hidden from Earth-based observation. When it emerges from conjunction in late November, researchers will face the task of interpreting observations of an object that may have changed dramatically during its invisible perihelion passage. The post-conjunction appearance may validate one of the current theoretical models, or it could introduce new puzzles that require entirely different explanations. The scientific debate surrounding Comet 3I Anomalous reflects the broader challenge of understanding phenomena that occur only on rare occasions, and push observational capabilities to their limits. Every model makes assumptions, and every explanation must account for the possibility that interstellar objects may operate according to physical principles not yet discovered through solar system experience. Part 13. Plausible, yet wild, explanations. Before we venture into the realm of truly speculative possibilities, science demands that we exhaust all natural explanations, however strange, that are still plausible. This comet may be beyond our current understanding, but it likely still operates within the bounds of known physics, just under extreme conditions never before observed in human experience. The dominance of carbon dioxide detected in its coma provides our first clue. This composition suggests it formed in a region of its birth star system, where temperatures were low enough for CO2 to condense into solid ice. This typically occurs beyond what astronomers call the CO2 snowline. In our solar system, the CO2 snowline is much farther from the Sun than the region where most comets form. However, other star systems may have different temperature profiles or chemical compositions, placing the CO2 snowline at a distance where significant comet formation occurs. The formation environment hypothesis explains not only its unusual chemical composition, but also its enhanced outgassing behavior. At the same temperature, carbon dioxide sublimates more easily than water or ice, potentially producing gas release rates several times higher than in water-dominated comets. This enhanced volatility could explain the rapid brightening and unprecedented coma size observed in September. However, a CO2-rich composition alone does not explain the sunward-pointing anti-tail. This is where dusty plasma physics comes in, introducing processes that operate at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena. When solar ultraviolet radiation ionizes the gas in a comet's coma, it creates a plasma. This ionized material interacts with charged dust particles in complex ways, which can produce self-organizing structures unlike anything predicted by simple gravity and radiation pressure models. When influenced by the magnetic fields carried in the solar wind, charged dust particles can form streams, filaments, and even spiral structures. Under specific conditions, these electromagnetic effects could overcome radiation pressure, allowing material to flow in directions that seem to violate basic cometary physics. The result could be an anti-tail structure pointing towards the Sun, while a traditional tail streams away from it. The rotation state offers another pathway to explain its anomalous behavior by applying conventional physics to extreme conditions. A very slowly rotating nucleus could develop extreme temperature differences between its day and night sides, thereby concentrating gas eruptions in specific regions. If its rotation is slow enough that its sun-facing side reaches much higher temperatures than experienced by solar system comets, thermal expansion and gas pressure could produce jets of material with high enough velocity to overcome solar radiation pressure in the sunward direction. The result would be a preferential ejection towards the Sun from the hottest regions of the nuclear surface. The green color that appeared in September also presents its own natural explanatory challenges. Diatomic carbon typically produces green emission in comet comas, but initial spectroscopic observations showed little evidence of other carbon-bearing molecules besides. However, a threshold hypothesis proposes that the release of diatomic carbon only became significant when it crossed a specific temperature or solar radiation threshold at its distance of 2 astronomical units. This process would require specific radiation conditions and molecular densities that may not have existed during its initial observations, but developed as the comet moved closer to the Sun. Variations in surface composition provide another natural explanation for its unusual behavior. It may not be a uniform object but instead contain discrete regions with different chemical makeups. As it approaches the Sun and different areas of its surface experience heating for the first time, these chemical variations could produce time-varying eruption patterns. The initial CO2 dominance might reflect the early activation of the most volatile surface deposits, while later heating could expose subsurface materials with different composition. Porosity and internal structure also influence cometary behavior in ways that could explain its anomalous features. A highly porous nucleus could allow solar heat to penetrate deeply, activating subsurface volatile deposits that are normally insulated from external temperature changes. The enhanced porosity hypothesis explains both the vast coma and the rapid brightness changes. The most likely explanation for its extraordinary behavior is a combination of these natural processes operating simultaneously. A CO2-rich composition drives the enhanced outgas. Plasma physics creates the anti-tail structure. Slow rotation concentrates activity in specific regions, and complex chemical processes produce the observed color changes. While each individual process is still within the realm of well-understood physics, their interaction under the extreme conditions of an interstellar comet encounter could produce phenomena that seem impossible from the perspective of solar system comet experience. Comet 3I Nautilus may represent an extremely weird comet rather than something fundamentally alien, but it is precisely this weirdness that makes it the kind of object that could revolutionize our understanding of small body physics across the galaxy. Part 14. Wild Speculations. Now we venture into the realm where science fiction meets speculative possibility, where the line between natural phenomena and truly extraordinary explanations begins to blur. While there is no credible evidence to support these exotic interpretations of Comet 3I Nautilus's behavior, the unprecedented characteristics of the comet invite the kind of speculation that has accompanied every unexplained astronomical phenomenon in human history. These ideas exist not as serious scientific hypotheses, but as thought experiments that illustrate just how strange our interstellar visitor truly is. The alien technology beacon hypothesis is perhaps the most persistent exotic explanation for unusual astronomical objects. Ever since the discovery of Oumuamua sparked debate about its artificial origin, each new interstellar visitor inevitably prompts speculation about possible technological signatures. In theory, its rapid brightening, unusual anti-tail structure, and enhanced coma could represent the activation sequence of some automated probe. The beacon scenario imagines it as a dormant technological artifact, remaining inactive during its long journey through the interstellar medium until it encounters conditions that trigger a preset activation protocol. The September brightening event could mark the moment when solar radiation reached a sufficient intensity to power up a dormant system, and the anti-tail structure could represent a directed energy emission or material ejection for some technological purpose. However, this technological explanation immediately faces challenges when confronted with the observational evidence. The spectral signatures clearly show evidence of standard volatile compounds, all consistent with what is expected from natural cometary outgas. No anomalous isotopic ratios, artificial materials, or energy signatures characteristic of advanced technology have been detected. The quasi-living plasma hypothesis ventures further into speculative territory, drawing on research into the behavior of complex plasma. Laboratory experiments have demonstrated that dusty plasmas can self-organize into structures that exhibit properties resembling biological systems. These plasma structures can reproduce, evolve, and respond to environmental changes in ways that are superficially similar to living organisms. Some researchers have speculated that such complex plasma systems could arise naturally in the space environment, potentially developing behaviors that mimic primitive life forms. In theory, its unusual outgassing patterns, anti-tail structure, and responsive brightening could represent the manifestation of such a plasma-based phenomenon. The concept of living plasma suggests that interstellar space might harbor forms of organization that operate according to physical principles entirely different from carbon-based biology. However, this explanation requires invoking physical mechanisms that remain purely theoretical. The purposeful scout narrative transforms it into an active reconnaissance mission from another star system, equipped with programmed behaviors designed to study the inner regions of our solar system. This scenario imagines the comet's unusual features as intentional design. The vast coma might provide sensor capabilities or communication range, while the anti-tail structure could represent a data transmission system aimed at a distant receiver. The Scout hypothesis suggests its brightening was not a random outgassing event, but a controlled activation of observational and communication systems as it approached its primary mission target. However, the Scout scenario faces the same evidentiary challenges as the technological beacon hypothesis. Its chemical signatures, thermal behavior, and structural features are all consistent with expectations for a natural object. The exotic matter hypothesis proposes that it contains materials not known to current science or operates according to unknown physical principles. Theoretical physics allows for the possibility of exotic forms of matter with unusual properties, dark matter interactions, modified gravitational behavior, or quantum effects operating on a macroscopic scale. Exotic matter could explain its unusual anti-tail through gravitational anomalies, or its enhanced outgassing through energy release mechanisms that go beyond conventional chemistry. This explanation allows for the existence of natural phenomena that are beyond current scientific understanding, suggesting it is not an artificial technology but a natural process involving physics that human science has not yet encountered. The speculation of a temporal anomaly enters the most exotic territory, suggesting it might represent some transfer of information or matter across cosmic timescales. Science fiction scenarios imagine the comet as a message or artifact from our own future, sent back in time using technology that circumvents the limitations of conventional causality. However, the scenario of time manipulation requires physics that is not only unproven but contradicts fundamental principles of causality and thermodynamics as currently understood. A critical perspective on all these exotic explanations emphasizes that seemingly mysterious astronomical phenomena often find mundane explanations once sufficient data is acquired. History suggests that Comet 3I Telix will ultimately find an explanation within the bounds of known physics, although it may involve processes or conditions not previously observed. The value of exploring these speculative scenarios lies not in their likelihood, but in their ability to highlight just how extraordinary Comet 3I Tellis is in the context of human astronomical experience. An object that can seriously inspire thoughts of alien technology, living plasma, and exotic matter represents something truly unprecedented in our understanding of interstellar visitors. As it continues its hidden passage to perihelion, these exotic explanations remind us of how much we still have to learn about the universe beyond our solar system. Whether the comet emerges from conjunction as a completely mundane object or continues to exhibit features that defy conventional explanation, it has already succeeded in expanding the boundaries of what we thought was possible for visitors from other star systems. Part 15: The Final Countdown. The cosmic clock is ticking down to a series of critical moments that will determine not only what Comet 3I Tellis reveals about itself, but also what it teaches us about the broader population of objects that wander between the stars. Each upcoming milestone represents a crucial test of our understanding, our observational capabilities, and our ability to extract meaningful science from a phenomenon that pushes the limits of current astronomical practice. October 3, 2025 marks the first critical node, its closest approach to Mars, This encounter represents humanity's best chance to maintain surveillance on it during the period when Earth's telescopes begin to lose sight of it. The robotic eyes orbiting Mars will attempt observations that were never intended in their original mission designs. Success or failure depends on variables beyond human control. If it maintains or enhances its current brightness level, the Mars orbiters might capture details invisible from Earth's telescopes. However, if the comet dims, even the most sensitive spacecraft instruments may only detect a faint signal. Late October brings the hidden climax, perihelion, on October 29th. During these crucial few days, it will experience radiation intensities that could trigger the most dramatic transformations of its entire solar system encounter. However, perihelion occurs almost exactly when it is most difficult to observe from Earth. A cosmic irony has scheduled the moment of greatest scientific interest to coincide precisely with the moment of lowest human observational capability. The observational gap will last until early November, creating a 4 to 5 week period during which it effectively disappears from human monitoring. The re-emergence in early December represents the next critical milestone, when Earth's telescopes will reacquire and track it. The comet that emerges from conjunction may bear little resemblance to the object that disappeared in October. The post-perihelion timeline extends scientific opportunities into the following year and beyond. A close approach to Jupiter in March 2026 may provide additional spacecraft observation opportunities. As it begins its final departure from our solar system, what we can learn from successful observations extends far beyond the specific characteristics of it itself. Interstellar chemical analysis provides a direct sample of material formed around another star, preserving information about chemical conditions across the galaxy. The already detected CO2-rich composition hints at a formation environment different from our local solar nebula. The study of cometary behavior under extreme conditions could revolutionize our understanding of material release mechanisms, dust dynamics, and plasma physics in extraterrestrial environments. The anti-tail phenomenon challenges fundamental assumptions about how cometary material responds to solar radiation. The scientific implications extend to broader questions about interstellar objects and their role in the chemical evolution of the galaxy. It represents only the third confirmed visitor from another star system, but its unusual features suggest that the diversity of small body formation in the Milky Way far exceeds the predictions of current theory. If it fragments during perihelion, the analysis of the fragmentation could provide unprecedented insight into the internal structure of interstellar objects. Different fragments might contain material from different depths of the original nucleus, effectively providing a core sample of an object formed around another star. Expectation management requires acknowledging the inherent limitations in studying these objects. It will likely never become a naked-eye spectacle for Earth observers, with its peak brightness, while within telescopic range, remaining invisible without optical aid. The lack of a dramatic visual display does not diminish its scientific value. Future detection systems must identify interstellar visitors years in advance to enable meaningful spacecraft encounters. Improvements in ground-based surveys offer a more immediate prospect for enhancing interstellar object science. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s with unprecedented sky surveying capabilities. It is expected to discover several interstellar objects per year once fully operational. This dramatic increase in detection frequency will transform interstellar object research from rare opportunistic observations into a systematic study of a population. International collaboration becomes increasingly critical as interstellar object research requires coordinated observations across multiple facilities and time zones. The broader implications extend beyond astronomy to fundamental questions about the nature of matter and chemistry throughout the galaxy. It provides direct physical evidence of conditions in other star systems, preserved in its pristine form over millions of years of interstellar travel. Astrobiological considerations also arise from the study of interstellar objects, as these visitors could transport organic compounds or even primitive life forms between star systems. While there is no evidence that it harbors biological material, its organic chemistry could provide insight into the distribution of complex carbon compounds throughout the galaxy. Planetary defense considerations benefit from the study of interstellar objects, which improves understanding of how such bodies behave under solar heating. Future interstellar visitors could travel on orbits that bring them closer to Earth, requiring accurate predictions of their behavior for impact risk assessment. Its unusual features highlight the limitations of current models used to predict cometary behavior. As it approaches the critical dates of October, Comet 3I Atlas has already succeeded in demonstrating that interstellar visitors will continue to challenge our assumptions about what is possible in the universe beyond our solar system. Whether the future behavior of this comet confirms current theories or introduces entirely new puzzles, it has set a new standard for the unexpected in astronomical phenomena. The final defining sentence of its legacy depends on what the observations of the coming weeks will reveal. It is beginning to reveal its true identity: a chemical time capsule from another star, a physics laboratory operating under conditions never before observed, or perhaps something more extraordinary that will force us to rewrite our understanding of what wanders between the stars. In the coming weeks it will either erupt with unprecedented brightness, fragment into a stream of interstellar debris, or slide quietly past our sun, carrying its secrets back into the darkness of the cosmos. Whatever happens could fundamentally change how we view visitors from other stars. For anyone able to follow this cosmic detective story, the call to action is clear. Watch for mission images released by ESA's Mars Express and NASA's Mars Reconnaissance Orbiter. Then await the post-perihelion updates from the Hubble and James Webb Space Telescopes, which may finally reveal what Comet 3I Atlas truly represents. The universe has sent us a messenger from another star, and we are about to find out what message it carries.